which provides a bunch of different network semantics. Right? So we've already seen 3, and they're all kind of done in this one module. So I think last time there was this question about what if I had a system and I wanted that one system to use it with different semantics and it was sort of all fixed the way we defined it in simple DS. So now we're doing it with type classes, so it's a lot more flexible, right? As long as you have the right handlers for the types of like the nodes and messages and state, you can get semantics for different fault models. So instead of module type, we're going to have a type class for the base params. And then we have different kinds of base params. So you remember when we tried to do fresh, we wanted to make a single node system. And it was kind of annoying because there was no real way to have the fact that there was no network I/O encoded. So we had the trick in simple DS where we just had an empty type for messages, right? So that we knew if ever anybody tried to hand us a message that was bogus. We just got false for free from it. So here we're going to be a little bit more careful and actually give semantics to single node systems, which is going to be useful for things like a key value store, for example, or for state machine replication. Right? So if you have a key value store, that really is just like a single node system, right? Like it's a map, right? And you distribute it to get availability and performance. So even though it's really dead simple, these single node things are actually pretty important and useful. What else do we have? Yeah. So we have some more parameters than we had in simple DS because there's just more kinds of failures. We are going to consider, we have semantics in here for networks that have crashes, right? And if you want to reason about a crash, things get tricky because you want to reason about, when I come back, what state am I in, right? So we have things like this reboot function, which tells us which parts of the state are persisted. And that's the state that you're guaranteed to be in, right? That part of your state is guaranteed to still be consistent when you come back. Again, it's a sort of atomicity. Right? I know that either the writes to that part of the state were successful or not. They never stop halfway. That's important because when I come back, I don't want to be in some weird inconsistent partial state. Right? I want to know that either the handler finished or it didn't. So we have these disk operations, right, which allow us to encode, these sort of things are for backup. Okay, and then we have this, kind of nice library that describes, step relations in general. You can find stuff like this. Adam was showing some stuff yesterday. There's plenty of stuff like this in the CompCert small step library. Here's another one in Verdi. And what's nice though, right, is that it's just these really simple encodings of like, what does it mean to be inductive, right? So for any step relation, if you have a property and if it holds in state A, and for any other state A can step to, right, for any trace, it'll hold in the things it gets to, then that thing will be inductive, right? So this is this definition. How do you know you got the definition right? Well, we prove it, right? We show that if it's inductive, then for anything that you can reach, that property will still hold, right? So we are confident we got the definition right. And we can do this for a bunch of other semantic facts. And then we get into the actual semantics, right? So here's stuff for single node systems. We'll talk about those a little bit when we look at VARD. But here's something that should look more familiar, right? So it's a little bit wider, and there's sort of more parameters. But we have a deliver case, right? And we have an input case. And if you look, you can see like, okay, well, look, if the network contains packet P, now here instead of using in, right, we've done it this way because it fits better with the list lemmas we have proved. This is another thing that's worth mentioning, right, is that the way you end up defining things, even if they're totally equivalent, often has huge consequences on proof automation. So the difference between using in here and building it with the explicit append and cons makes a lot of things just go through for free for us. Right? Somebody else in a different way of doing it might have used in more, and it would be this would be very painful, right? You'd have to sort of transform this to an in fact everywhere. This is also why it's hard to change big systems, because these little seemingly inconsequential design decisions, a lot of stuff ends up depending on the way you define that, right? And so if you try to change it, all that stuff that depends on the way you define it suddenly breaks. Right? If a bunch of places you relied on the fact that you needed to have an equality of this shape, right? And now all of a sudden everywhere that you need an equality of that shape, you have an in instead, you're going to have a lot of LTAC hacking to do. It's very unpleasant. So this gives us, the fact that the message is in the network, and then, this is how we run the handlers. We construct a new network. Input works the same way. Here's the other way of doing duplicate steps, right? So here, we're saying suppose some message is in the network. When we duplicate, we put a copy of it on front. Right? So the thing that's different or nice or whatever about this is that now the dupe step matches the async step very closely. It just has one extra rule. And what does that mean? Well, that means that if you had proofs about certain cases for your system, they're just going to work unmodified because these two constructors are the exact same. Right? Does that make sense? So as constructing these cases, I just can copy and paste it. It'll just work. So there are trade-offs here, right? Now, on the other hand, I have another case, another rule. So it feels clunkier, right? It feels less concise, less parsimonious. But these are the kinds of trade-offs that when you build bigger stuff actually matter, right? They have these sort of far-reaching consequences. We also have drop, and here we have more interesting semantics. So here we have a semantics where nodes can actually fail. And the deliberate input cases, drop and duplicate, basically all work the same. There's also this case, right, which just adds any host to the set of failed hosts, right? And as you'll notice above, right, to actually get a message or to get an input, you have to not have failed. So this semantics just lets you, completely obliterate a node, right? Nothing can interact with it. It's just gone. You can also resurrect it. So there's this reboot case for something that's in failed. What do? Well, we're going to bring it back based on it, what it specified from its state that gets saved, right? So the parts of its state that are persisted to disk are recovered. Everything else is, sort of havoc, and that's it. And then there's a few other semantics, but the one that's, so this is the same as the failure, but there's disk operations as well. These things start to get big, right? So this is now what, like 2 buffers full, whereas in CNUM it was barely 1 in a bigger font. These things start to be more and more tricky. This semantics with failure, though, is really kind of the star, right? This is the one that a lot of stuff is designed in practice around, this sort of asynchronous, semantics with failure. Okay, what else in net? Yeah. So hopefully that's not too weird. So when you guys are looking at Verity later, you should just remember that net.v is a lot like netsem. It's just that there's more cases in the constructors. There's more constructors for the semantics. There's more kinds of steps. Okay, so another thing that hopefully isn't too unfamiliar is that we can go look at an implementation of our counter system. But instead of doing it in terms of our simple DS, this is a version of counter in Verity. Right. And again, it just has primary backup. It has increment and ACK messages. There's no modules anywhere, and that's because we're going to do this with type classes. We write handlers in much the same way, right? So you see the same use of the notations we had before. And that's about it for defining it. And then we can sort of instantiate it to get an actual system. Right? And then we can we're going to prove a bunch of helper lemmas. And then we're going to sort of build up. And all of these lemmas basically have the same flavor, which is that after you run the handler, something continues to be true, or something, the fact that a handler returns a certain value lets you conclude some fact about the system. So let's just go down the final proof. Right. So yeah, it's not the only one. Yeah. Yeah. So basically what we know is that this is that invariant we proved last time, right? Which is that the difference between the state between the primary and the backup is exactly corresponds to the number of messages in flight. Right? So the degree to which the backup is behind the primary is equal to the number of increment messages from the primary that are still waiting in the network to be delivered. And then once we have that, we can prove the final. This is a trace-based spec, which is something that was in the suggested exercises for yesterday, which is to just show that we never have more outputs than inputs, right? And we should also probably strengthen it to be unique. But okay, so that's something that we saw before. Let's look at a system that we did not implement yet in simple DS. So this is a key value store that we're going to formally verify. My students named it Vardy just to troll. It's been very frustrating, right? You never quite understand what they're talking about. But it's actually pretty simple. So this is going to be a single node system. And what clients can do is they can ask to basically set some key to a value, to pull the value of some key out, to delete some mapping, right, to remove it, to do some compare and swap, and to do some compare and delete, right? And we'll see what the semantics are in a minute. But one quick question, it seems a little bit weird. I mentioned that this is going to be a single node system. So why do you have compare and swap? Yeah, exactly. So, two clients also want to know about each other. So even though they're sort of forced to go through the same node, right, they might want to, get some guarantee about the way that they're using the key value store and to be able to reason about that. Okay. And then we only have sort of one output, which is, we respond, and, all of the requests are about a key, and then we respond with two options, and sort of, they represent some result to that query. And our system is basically just going to be a wrapper around a mapping from variables to values. We're going to reuse that. I guess I can show you. We just have this sort of mapping type in a module, right? So this is just like a regular Coq data structure where you can, it's like a hash table, right? So all we're doing is we're making a hash table that's accessible on the network. Okay, so we define all of our base types like normal, and then we're going to, build up a bunch of actions to handle these input requests from the client. And that works, just the way you want it to. It's pretty simple. So if somebody asks for the key, we do a lookup on it. So we defined a get k. We define get k above. It just does a lookup in the map in Coq, and we send whatever we got back to the client. If we're asked to do a put, we're going to get whatever is there right now. We're going to set it to what the client asked us to set it to, and then respond to the client with the old value. If we're asked to delete a key, we're going to do that as well, and we send back none because we have to put something there in this case. And then we also have compare and swap, right? And so this tells us what we mean by compare and swap. So basically, we get the old value out. If the old value is the same as the thing we're asked to set it to, or what the compare and swap said, that the test was for old value, then we're going to set it and respond, indicating that we've done it Otherwise, we respond with the old value, and the client will be able to tell because they know that the thing it asked us to check wasn't the same as the thing they got back, right? So they can see the difference. And we have the same thing for delete. Okay. So once we have that, right, we really just have to handle inputs, a single node, and we have a functional version of the same handler that we're going to use in the spec, right? So this is a theme that you see over and over in verification, which is that you have some sort of low-level code that's stateful or imperative, and you're going to rewrite it in a functional version that's a lot easier to do proofs with because things simplify. So we're doing that exact same trick here. And then we can basically say that the set of I/O interactions in the trace, right? We just sort of replay the trace, and we go through that interpreter, and so that gives a spec for what the client should see from us. So this system is kind of like our fresh system. It's a single node system. It's very simple. We can give a characterization of this key value behavior. It turns out that the proofs still end up being a little bit nasty because it's tricky to verify imperative stuff. But what's really interesting about Vardi isn't the single node system that just handles requests from clients. What's interesting about it is that we can take that system and we can apply a system transformer, right? So now I can take my key value store, which is something that gets used a lot in front of databases and other things in the web, and I can get some redundancy for it, right? So I can build a primary backup system. So I'm going to have 2 copies of the key value store, and it's going to be like the counter system where the primary is only going to respond to clients when it knows that things have been replicated to the backup, right? Except instead of just being a NAT, we're going to be able to do this for any kind of system, right? Including our key value store. So now we can have this sort of fault-tolerant key value store, even if, as long as these 2 machines aren't physically in the same place, even if a meteor hits, if it doesn't destroy the whole world, right? 1 copy of your data is still up and running. Yeah, so this is a lot like what we saw in sequence numbering, but again, sort of just in type classes. We're going to have 2 nodes, primary and backup. And let's go to the handlers to see how those work, right? Oh, let's look at state, sorry. Yeah. Okay. So we're going to have some underlying system. We have messages that we exchange, which look a lot like the counter system. We have state, which has some queue of operations to do, and then it has the state of the underlying system, right? So we wrapped it similar to the way we did in seqnum. One of the things that is different in Verity is that all systems come equipped with a list of all the nodes participating in the system. That's something we don't have in SimpleDS. That enables you to do things like broadcast, right? So if you want one node to be able to tell every other node in the system some news, you can use this list to achieve that. Right, and then we have sort of the initial state of the world. We have some actions that are going to help us implement the handlers, and then we have the input handler. So if the primary gets a request from some client, it's going to basically forward that to the underlying handler and do the right thing. Actually, we also hear if if anybody gets a request for read, right? Either node will do the right thing, and then here we similarly have the handler. But again, in all these systems, right, what we're doing is we're trying to simulate another distributed system so that it tolerates faults in a more adversarial model. Right.